course. Cool. So good morning, good afternoon, good evening. Uh, I don't. You might be joining us from many different places. I'm Rick. I'm Rick Perche. I am a PhD student at the University of Waterloo, Perimeter Institute, and the IQC. Um, the this course is supposed to be a course in RQI. Now, RQI stands for Relativistic Quantum Information. The and when Nicholas contacted me and asked me to organize this course, I said that it wasn't possible to deliver a mini course in RQI because RQI is a very diverse field. Probably it's one of the most diverse fields of theoretical physics right now. And then I offered to try to do a course on um, relativistic quantum information protocols in quantum field theory, basically, which is something that's a little bit more restrictive, and at the same time, it's something that I can talk more about because I am more of an expert in this than I am in uh, all of the other topics that RQI has, right? So let me just share screen real quick before actually starting. So if someone asked me what is RQI research, I would say that it's research that is related to research being done by people who are a member of this ISRQI. There's the International Society for Relativistic Quantum Information. The and if you do research related to this, you should most likely affiliate yourself to this society. We again we're a big community, so that's why there's a lot of different kinds of research being done here. Don't take whatever I am saying here to be a representative of the whole research that everyone is doing. There are lots of different things going on. There are lots of things that I would not be able to talk about, and I won't be able to talk about much. It's a fairly short mini course. So yeah, visit the website. It's isrqi.net if you want to learn a little bit more about the society. The Cool. So again, let's actually start. But this course about relativistic quantum information protocols in curved spacetimes. Let me just set up things here. I've never tried to do this, so if something goes wrong, I have some plan Bs and things like this, but hopefully it's gonna work. Let me take a look. All right. Cool. All right. So before I start, I think that the all right. So let me at least write the title before I say anything else. So my notes. All right. So right, the title of this course doesn't really matter. Names are names, but I will call it quantum information protocols in QFT. You can add a relativistic in front of it if you want. I don't really mind, but I think that the main point is that our goal in this course it is to couple local probes to quantum field theory. To a QFT and implement quantum information protocols. So this is our main goal. And now, before starting to do this, we need to kind of like set some I don't know ground rules. We have to talk about some certain topics which are not as interesting as actually doing this. The so Another apology is that today will definitely be the most boring class. Okay, today the goal of the lecture is to go over some background, to review some things that Nick talked during his course, to talk a little bit about quantum information and to talk a little bit about some other things. I don't think that the lecture today will last for 2 hours, but let's see. It really depends on the pace that I go. Um, Before really starting going through the goal of today's lectures, I would just like to say that if you enjoyed Nick's course, it's about like quantum field theory and curved spacetimes, and you enjoyed seeing the whole mirrored field operators and the well 2-point functions and how to define these things, I would argue that this course is a natural follow-up to that. Like, we're going to use a lot of algebraic quantum field theory in this course, and we're going to really do some calculations using these things. So I would say that this is a very natural place to go after that. But yeah, the let's start. So basically I'm assuming Nick's course, but it's not really necessary because I'll give most of the important information. And again, if you don't like this lecture, please don't give up on the course. Try the next lecture where we're actually going to do interesting things. So again, this lecture we'll talk about the background, just about the things that we will be using throughout the course. So background. So we're going to talk about three main things. One of them will be a brief review of QFT in curved spacetimes. Basically, we're going to talk about, we're first going to set the basics and the notation that we're going to be using, which might be a little bit different from what Nick used or not. Really depends on what he used. Then we're going to talk a little bit about some properties of the propagators. And these will be very, very important here. We're going to use these properties of the propagators to do pretty much all the calculations that we will be doing in this course. We're not going to use the basis expansion of the quantum field at any point, pretty much, in this course. Every single calculation will be done within the formalism of algebraic quantum field theory, and using like a general representation for the field without even actually picking a Hilbert space. So everything will be in terms of the 2-point functions and things like this. Then I'll briefly talk about quantum information protocols. I'm not really going to go into detail over what's over specific QI protocols or anything like this. I'll just mention the specific things that we need to know in order to do the calculations and to study the things that we'll be interested in studying. So basically we're going to talk a little bit about mixed and pure states. And we're going to briefly talk about entanglements, which we will be very interested in, especially in the context of quantum field theory. And finally, we'll talk almost nothing about quantum channels, just the bare minimum that will be required. And then the third thing that we're going to talk about is something that is kind of unrelated to these other two topics, but it's going to be important to define these local probes that we're using to probe the quantum field, right? So this third thing are Fermi normal coordinates. And basically, we're going to review the construction of the Fermi normal coordinates, and we're going to review some applications, let's put, and properties. But yeah, okay. So this is basically the plan for today. This is the only day in which I'm gonna write an organized plan here, just because the three topics are fairly unrelated in principle. But again, today is the background and setting the basics and the notation day, so it's not supposed to be, yeah. Can everyone hear me okay? Can everyone see everything that I'm sharing and everything okay? If I have any issues, please let me know. I'm assuming that everything is working. Cool. So let's talk about QFT and curved spacetimes. And this will be like a lightning review of most of the things that Nick said, and I'll say some things that he didn't. If you didn't attend his course, that should be okay, in the sense that basically if you just accept everything that I'm writing here, you should be able to follow everything else. But if you did, then you have a better understanding of everything, of course. So we will focus in the case of in a scalar field, it's a real scalar field, in a background spacetime. So let's in a background spacetime M, say. Then you can define the quantum field theory, whatever. Everything that we do basically can be generalized. Okay. And if you want to generalized, and if you want to learn more about how to define algebraic quantum field theory in curved spacetimes for more general fields, whatever, there is this textbook which you can get legally for a lot of money or illegally in many places where probably you know how to get them, which is called Advances in Algebraic Quantum Field Theory. This there are many authors to this book. I'm just going to write one of them, which is R. Brunetti. If you look for this, you should be able to find it. And especially look at chapter 3. Chapter 3, which is where fields of higher spin and curved spacetimes are defined. If you don't, that's okay. But if you want to generalize everything that we see here for different situations, whatever, take a look at this. It should be fairly straightforward to generalize most of the things. We will always focus, or we'll always consider a specific example of a QFT. When I say specific examples, because in principle you have the algebras of observables that have to satisfy whatever. In this case, we're going to consider in this case, like we're going to consider the case where the field or where the algebra can be built from basically the association of the test function. So basically that this association of f into these smeared field operators phi f, right? Such that the f's are a completely supported function and smooth in M. This condition here, I'm going to say that it can be relaxed. You can always consider, for instance, Gaussians, other smooth functions that are not really completely supported. And M is the spacetime that's already set up there. Okay, cool. So, basically this association has to respect a couple of rules. Hopefully you've seen this with Nick. So such that this mapping here is linear, such that if you conjugate, if you take the dagger of your phi f, this is equivalent to starring your f. Basically this because it's a real scalar field theory. Now, if, okay, so phi of pf equals 0, which is basically the equations of motion, where this p is the differential operator from the equations of motion. From the equations of motion. So, e.g., p could be the Laplacian, or nabla mu. Let's write the D'Alembert here instead. Could be the D'Alembert for the case where you're you have a massless Klein-Gordon field or something like this. Okay, let me make this a little bit better. The other important thing is how the elements in the algebra commute. which is basically that the commutator of phi f and phi g will be E of fg, and this is the first propagator kind of that we are going to see here, where this E of fg is a double integral over m cross m prime dv dv prime. Dv here is, of course, the root minus g d4x, and the what you have basically is the integral of this kernel E of x x prime, which is the causal propagator. That's how we call this. And of course, it's given by the retarded Green's function minus the advanced Green's function. Now, there are many conventions here that people can use. Some people like to define this as the advanced minus retarded, and that is okay. You would think that if you did this, you should add a minus sign here in the I. But there's another alternative to this, which is basically how you define your Green's function. So just to so this is the advanced Green's function, and this is the retarded Green's function. Okay. The thing that you can do in order to not pick up the sign there and to change these things, it depends on how you define the equation of motion that the G satisfies. So basically, remember that P is the differential operator. If you ask PGR to be equal to delta or minus delta, you're going to change the sign of your retarded or advanced propagator. So all of these conventions work if you apply your differential operator to the retarded or to the advanced in one of the components, and you get the delta, where this delta here, this delta is the delta for x prime with all of the included factors of root minus g and everything. So this is basically the such that if you integrate it, well, let me write this properly. So this is the function such that if you integrate dv prime f of x prime delta 4 of x prime, you get f of x. Now, although the retarded and advanced propagator dissatisfy the same equation of motion, there's something very important, which is that if you fix a point x, and now you look at the points x prime, what happens here is that the retarded propagator of x prime, it only has support in the forward light cone of x. And the advanced propagator of x prime only has support in the past of x prime, of x, basically in the causal past of x, okay? And this is super important. This is going to really like be used many times, used and abused during this course, okay? But basically with this, we have the definition of the quantum field theory, right? It's an association of completely supported smooth functions in spacetime to operators. And this builds the quantum field theory. Just to set some notations properly here, the overall, if A is a bidistribution, there are a couple of things that you can do with this. There are two things that you can do with this. And we will basically denote, so AF basically will mean to us the function AF of x, which is the integral dv prime of f of x prime a of x prime. So this would be, you use the a as a linear operator. So you just like integrate with respect to x prime. But what you can also do that we've been doing up there was to say that a of fg is the integral dv prime, and now you're going to have two arguments here, right? So just whenever I write gr of fg or whatever, this is the integral over space time volume of the retarded Green's function or the advanced Green's function or whatever. So hopefully this, yeah, just be aware of that. That's a notation. And this quantum field that we defined, basically it can be seen as this smeared field operator, right? So the quantum fields, or the, say, the smeared quantum fields, or the phi hats of F, can be seen as this as an operator value distribution, basically. This is not really formal technically, but the idea here is that this kernel of this operator value distribution is the quantum field. So it's, let me see, phi is an operator valued distribution. And this is how you would relate this with the standard quantum field theory that you would have in, well, usually, right? Cool. Now, how do we actually build the algebras of observables? So we have algebras, which I'm going to denote A of O, which are local algebras, where O is a subset of M, are built by simply considering products by multiplying the phi f's that we have and performing linear combinations with them. Under the assumption sorry, let me do this properly. Sorry, the computer lagged a little bit. Hopefully it didn't chop too much. Under the assumption that the functions f, so that f's belong to C, 0, infinity, O. So basically f is just a function defined in the set O with supports. So basically this is the supports of f is contained in O. Okay. So f is only non-zero inside O. Okay, cool. All right, states. And okay, so states. A state, omega, is a linear function omega from A to C, such that two things happen, such that omega of the identity is 1, which is basically equivalent to the trace condition that we have for density operators, trace 1. And the second condition is that omega is positive, and this means that omega applied to any A dagger A is larger than or equal to 0. Okay? And this is, of course, for every A in the algebra. So for every A in the defense here. Okay, cool. And the idea here is basically that a state maps observables into expected values. Okay. All right, nice. Oh, nice. So, just a comment here, which yeah. So, oh, this is okay. Let me just adjust the. So, in this course, we will not pick the basis of solutions. UK of x and expand the field S phi of x integral d3k UK of x ak plus UK of x star ak. So hopefully you've seen with Nick that this can always be done whenever you pick a vacuum state, then there's the GNS representation associated with it. And if you use this GNS representation, it can always be the Hilbert space and whatever. And then there are many conditions here and there. Well, in the end, we're not going to have to do this. We're going to do everything at the algebraic level, which is nice if you enjoy Nick's course, because we're really going to use the things that are there. But on the other hand, although we're not going to do this, something that we are going to do is that we are going to mostly, so we will mostly restrict ourselves to Gaussian to zeroing Gaussian states. What I mean by this is that basically, so these are states such that if you have omega applied to an odd product of field operators of 2n plus 1, this is 0, and such that Wick's theorem applies. So you can always expand the even correlators in terms of the 2-point function, basically, and such that Wick's theorem applies. Cool. So basically, every state omega defines a correlation function. Basically, this correlation function is a bidistribution. So the idea is that if you apply the states to a product of phi f, phi g, this defines this distribution W of fg, which is the Whiteman function. And this can always be written as a double integral of f of x prime, sorry, g of x prime. So g of x prime times the W of x prime. And this is what we call the Whiteman function. And for the states that we're going to consider, an extra restriction. It's not really like a restriction, this extra property. Oops, an extra property is that if you consider W of Fg minus W of GF, this will give you I times E of Fg. And the reason for this is the commutator, right? So this exercise proved this. Exercise prove this. So hard to prove. It's just you're just gonna rewrite this as the commutator, then you're gonna use that omega of the identity is 1. Everything's gonna work. If you can see this right away, of course, there's no need to do the exercise. There's never need to do the exercise, but yeah, it's useful. Cool. So this means basically that the imaginary part of the Whiteman function is one half this E of FG, right? Because if you divide this by I, then the two sides of whatever. So basically, this means that we can write the Whiteman function, the kernel of the distribution, as being, I'm going to write it as one half h of x prime for reasons that will become evident soon. Then this I divided by 2 and the E of x prime, which is the imaginary part of the Whiteman function because of the other one, because of the previous expression. And now this H here is also, it also defines a bidistribution. So this H of f and g is the expected value of the anti-commutator of the field. This it's symmetric. H of x prime is h of x prime x, and it's real. And this is what we call the Hadamard distribution. Cool. So we have three propagators so far, or three two-point functions. We have the Whiteman function, the causal propagator, and the Hadamard distribution. We're going to define our fourth and fifth propagators now, which are the Feynman propagator. Both these will show up later in these. So the Feynman propagator and X prime is there are many ways of defining this. The way that I'm going to define this is as theta of t minus t prime w of x prime plus theta of t prime minus t w of x prime x. This basically is the expected value of the time-ordered product of phi of x and phi of x prime. That's the idea behind this, okay? T is any time parameter, and theta is the Heaviside theta. So for any time parameter T, and this theta here is the Heaviside theta. Okay, cool. So have you discussed the Feynman propagator in the quantum field theory and curved spacetimes course? For anyone that was there? Is there any way in which people can communicate? I don't know. Maybe I can't hear people. Are you people speaking? Okay, I'm confused now. So can someone put something on chat just to make sure that everything is working properly? All right, thank you. Okay, thanks. All right, great. So the Feynman propagator, right? Nice. So if you have seen the other propagators more than the Feynman propagator or something like this, there's some important properties that the Feynman propagator satisfies, and it's a good exercise to try this. One of them is that GF is independent of the specific choice of the time parameter. Another one is that the Feynman propagator is actually symmetric. So gf of x prime is the same as gf of x prime x. The other one is that the Feynman propagator can be decomposed as 1/2 the Hadamard distribution, so the same as the Whiteman function. But here we get another term, which is this delta of x prime. And this is the fifth propagator that we're going to talk about. This delta of x prime is the retarded plus the advanced propagator, or Green's functions, right? So, and of course, this is symmetric. The way to see that this is symmetric, just notice that GR of x prime is actually G of x prime x. So to propagate from x to x prime with a delay is the same as to propagate from x prime to x, but going back in time. That's the idea here. Okay. Cool. So this is almost everything that we need from quantum field theory that will show up later. The last final things are that are just properties of expected values of operators and things like this. So let me just list them here. And if you're familiar with them, then that's great. If you're not, try to show them if you want. The first one is one that I recently discovered that ChatGPT is able to prove this, sometimes correctly. So if you take the expected value of e to the I phi of f, this will result in e to the minus 1/2 w of ff. So yeah, or of course, because sorry, yeah, or and this is 1/4 h of ff. The other one is that I should have probably mentioned this sooner. If you conjugate let me write this more. If you conjugate the Whiteman function, so if you consider w of x prime and you conjugate this, you get w of x prime x. So to conjugate the Whiteman function is the same as switching its arguments. And now this means on the smeared level that if you consider w of fg, and now you conjugate this, now you get w of g star f star. Because you switch the arguments of the w and you conjugate everything that is within this expression. Okay. So yeah, showing this is always useful. E of x prime is antisymmetric, and this is basically what grants us the property above. And this means that in this mirrored level, if you have E of fg, this is minus E of gf. Then the Feynman propagator, we already said this before, but yeah, this is symmetric. And on this mirrored level, this means that gf of fg is the same as gf of gf. That's a funny thing to say. And finally, the delta of x prime. Again, I said this before, but this is the list of the important symmetries and properties of the propagator. So always good to have this one here. And we're going to be using these throughout a lot. Cool. So now the last thing that I will define, just because it will make it more convenient to do some of the calculations, is it's a modification of the Whiteman function. So we'll also define the time parameter dependent distributions So now if you give me a time parameter t, I will define wt of x prime, as being theta of t minus t prime times w of x prime. So I'm chopping just the upper part of w, and w minus t, slightly, well, it's a bad notation, but what this is basically flip the arguments of the w. And the good things about this distribution here is that the final propagator is just going to be, well, I don't even have to write the, well, okay. The final propagator will be w minus t, and the Whiteman function is plus w minus t star. Because if you conjugate this, then you flip the arguments on the Whiteman function, then you use the, yeah, let me write this. So because basically the Heaviside state of u plus the Heaviside state of minus u is 1, and because w star of x prime x is w of x prime. And if you use these two properties, you can see that's reasonably easy. Okay. Just a final remark about quantum field theory will be this: it's that w star of fg is not the same thing as w of fg star, because w star is w with the flipped arguments, right? So this term here would be the integral of dv prime f of x g of x prime w of x prime w star. This would flip the arguments, and then you can do a change of variable. So this would be a w of gf. And on the other hand, the one above here, the w of fg, if you conjugate this, now you also have to conjugate the functions and to switch the arguments. So it's not there. These are not the same thing. So be careful with this. This is the notation stuff. But cool. These are the important properties and things that we're going to be using about quantum field theory. There is a reasonable amount of things, but it's not that big. Sorry about making this so small. I'm just like checking the length. But basically, yeah, this is what we're going to use from quantum field theory. Okay. Any questions regarding this? Can either leave them on chat or unmute. I'm not really sure how this works. Hopefully you've seen most of this in the QFT Curved Spacetimes course, and we'll be using all of this in this course. And again, apologies for how this looks like I'm just listing things thing after thing, but I thought that it would be better to just like give this overview in the beginning and then really do the course after than to stop every single time that we needed anything like this and then going through it, because I think that we wouldn't have enough time to do all of this. The next class, we're going to use absolutely all of these properties, and well, most of them, and do some actual calculations with this, which are related to protocols and curve spaces. Cool. So the next step then is quantum information, and I'll try to be quicker here. Okay, so I don't know how familiar people are with quantum information. I am sure that this is not a topic that has been really covered in the other mini courses, so that's why I wanted to say something about this. So I think that the key thing is that we want to talk about entanglement and we want to talk about quantum channels. And yeah, let's basically do this. In order to do this, I'm not going to use the context of quantum field theory. I think this complicates things too much for no reason, or it's just literally the same thing. So let's talk a little bit about states. Okay, states in quantum theory. Now, if you learned quantum theory like probably most of us did, then a state was simply an element of the Hilbert space such that and such that they very quickly found out that every single state that differed by a phase didn't really change at all, right? If it's a single state, then it doesn't affect anything. Now, also, then probably you were introduced to density operators, right? So operators that act in the Hilbert space, and these are positive operators, and the trace of these operators is one. And then in the algebraic perspective, you see states as these linear operators that map linear functionals, whatever, that map operators on the Hilbert space into complex numbers, such that, again, omega of the identity is 1, and omega is positive. Okay. And of course, in quantum field theory, you just replace this with the algebra of observers, like we just did, right? And each of these is more general than the other. So than the other. What I mean by this is that basically well, if you have an operator in your that acts in your Hilbert space, then the omega A, well, the idea is if A is an operator that can be represented that is acting in your Hilbert space, then you can compute omega of A. And this would be the equivalent of computing the trace of rho A, where rho would be the density operator, right? Now, the idea is that any density operator in a finite dimensional Hilbert space can always be written as a finite sum of unidimensional projectors in different directions, where the sum of these PIs is 1. So it's basically a convex combination of the of one-dimensional projectors, right? Convex combination. And the idea is that if we are in the case where our rho is a pure state, then the trace of rho A just becomes the expected value of A with respect to the adjacent brackets, right? So this is how one is more general than the other, right? Now, the idea here, which will be key to many things that we're going to do, is that of a pure state. So pure state is a state omega such that omega cannot be written as non-trivial combination. So it can't be written as a linear combination of other states. So basically, then the non-trivial is not necessary, but um, it's an extreme of point in the set of states, right? You can't write this as a complex combination. But, yeah, this will be a central concept, and basically the idea here is that if you have a mixed state, you can interpret this as a classical ignorance or some sort of ignorance about your state itself. So if you have a mixture between two pure states, basically the idea is that you have this combination between you have certain probability of having one state and a certain probability of having another state, and you have this uncertainty, which might have come because there are correlations between this state and other states that you're unaware of, or it might have come from the fact that it's simply your ignorance about something regarding this state. Okay, and we're going to see how this is related to entanglement soon. But before this, let's talk about multipartite systems, because this is basically um, where we can start talking about entanglements. And I wish that I mean, you can teach a full 5 lecture course about entanglement. I don't have that much time, so just try to be brief. So, given two quantum systems.
Sorry, can I interrupt regarding the previous discussion?
Yes.
So, not every type of algebra has a density metric structure, right? Or like, for example, the type 3 Von-Neumann algebras, they do not have this density matrices, but they do have the notion of omega, the
Yeah.
state.
Yes. And
So
that's
how
why
is
like one is always more general than the other, right? So the omega is the more general, then you go to the row, then you go to the vector,
Oh, I see.
to the
As you go down, you get more okay, okay, okay.
yes. The more general is the omega, then it's the row, which in the case where you can write your A acting in the Hilbert space specifically, then the omega of A becomes the trace of row A. And so basically I'm missing an if, I guess, in my statement. It's where's the it's like if A belongs to your A is an operator in the Hilbert space, then you can reduce it to that. Yeah. That's the idea. Thanks for the comment. Nice. All right. Okay, so multipartite systems, right? So given two quantum systems, again, I'm not going to go to the algebras or anything like this. I'll stick to Hilbert spaces in this case. I think it's again too much to go down there, and we're not going to need this in this case. So represented in H1 and in H2, the composite system. So the system, the two systems, is represented in the tensor product. So it's H1 tensor H2. Okay. Now okay. What happens here is that if you have the basis, so if phi n and psi m are basis for H1 and H2, then the basis for the tensor products can be written as phi n tensor psi. This is true for finite dimensional Hilbert space, but also for infinite dimensional ones. But for all purposes, you can think that that everything that I'm doing here is for finite dimensional in this quantum information sections. So this is the basis for H2. Now, the key idea of entanglements, or yeah, the key idea of entanglements is basically that let me write this in color. The key idea here is that the if that belongs to the tensor product Hilbert space, it's not true that the states can be written as a product of as a tensor product of two states in H1, right? And hopefully most of you are aware of this, but basically the idea here is that this is the key concept of entanglement, the key mathematical concept that gives us entanglement. So it gives entanglement. So how do we qualify the statement properly, right? So in the context of vectors, a pure state that can be written as V1, V2 is called a separable state. If you want to generalize this to the case of mixed states, so a mixed state is separable if it can be written. So you could think that it would just be that rho equals, say, rho 1 tensor rho 2. But this is not the case, because you can always have linear combinations of these. So can be written as rho being a sum, so a convex combination of rho I tensor sigma, basically. So it's not only products, it's products and convex combinations of products, because convex combinations of products, it's not going to increase the non-separability or the entanglement, basically. And the definition of entanglement is basically, well, a state is said to be entangled if it is not separable. And it's that simple. It's a state is entangled if and only if it's not separable. Okay. Now I must say here that entanglement is super important. So basically, entanglement allows for many different protocols, which would not be possible in classical physics or in classical information. A couple of examples, which I'm not going to enter in detail into, are secure key distribution. So basically, you can make sure that you're only giving the key to who you want to get, and you can make sure whether the code was cracked. Quantum superdense coding, which allows to effectively get more than one classical bit using one qubit, but yeah, which is something that maybe more people are familiar with. Things which are only possible. Right? The key question is how to quantify entanglement. Okay, whether an entangled state or not is defined here, but how do you quantify how much entanglement you have? Okay, so the key question is how to quantify entanglement. And this is a hard question, and we don't have a definite answer for this. Yes, sorry, there's a question. Please go ahead, unmute.
Yes. Excuse me, I have a question about the Hilbert space, H1 and H2 that you said and mentioned that to be entangled. I want to know that the conditions of two Hilbert space must be the same or not. It's not related to the conditions of the Hilbert space. For example, H1, H2. Because I think that when we have the two different spaces, is it possible that still we have a entangled or not? Thank you.
Yes, yes, the same everything, nothing that I said here implies that H1 and H2 have to have the same dimension or be the same Hilbert space or anything like this. You can do the tensor product between any two Hilbert spaces of any dimensions, can be infinite dimensions, but enumerable. And everything that I said here also apply. Sorry, I was missing the the does not imply that. I don't know if it didn't catch when I stroke it, but yeah, very important here. The cause of entanglement is the fact that not every vector in the tensor product is a product between the two vectors, right? The cool. Hopefully this answers the question. But yeah, the Hilbert spaces here are completely general. Nothing here depends on the Hilbert spaces themselves. But yeah, so coming back to the question of how to quantify entanglements. Yeah, this is a hard question. Okay, this is hard. We don't have a definite answer for this right now, in all cases at least. However, we can say some stuff in some cases. Okay, so an example is that for pure bipartite states, we actually can do something. So we can use the von Neumann entropy. So I'll define it very soon, but the idea is that you can use this, and this is an entanglement quantifier. All right. So what is this von Neumann entropy, right? So basically, what the key idea here. Oh, this is not good. Okay, it's back. Okay, so the key idea here is that if you have a pure state, right? So you can always take so if you have a pure state, then you can define the partial states in system A by tracing over system B. And of course, we can define the partial states of system B by tracing. The von Neumann entropy is defined as minus the trace of rho log rho. And in this case, basically if you have a rho which is of the form sum over I of pi, the psi i's are orthogonal orthogonal pure states, then oops. Okay. Okay, this is not good. The one node crashed. Okay, it's almost back where it was. That's good enough, I guess. Sorry about that. Let me just put it back to where it should be. So it's annoying. All right, so I'm just gonna quickly write again. Oh, okay. Sorry about that. I'm gonna quickly write the things that I had here before. So it's just that you can define the partial state by tracing over the other system. It can always be done. You can do this for both sides, both subsystems. The von Neumann entropy is just minus the trace of rho log rho. And now the key thing here is that if you have a rho, which is the sum of pi psi I, then the von Neumann entropy here of this rho is going to be just the entropy of the probability distribution associated to the pi's, which is the sum pi log pi. And this quantifies basically uncertainty. Okay, I'm going to put it quantifies uncertainty. There are many ways of seeing entropy, but let's just very vaguely say this, or how much information is missing, basically. That's the idea. And now, so if you have a pure state, so S of pure state, S of rho is 0 if rho is a pure state. Because there's no uncertainty. You know exactly where the state is. It's not a combination of states with different probabilities, okay? But S rho is non-zero for mixed states. Now, what this means, basically, is that if you were with a pure state to begin with, now you traced one of the systems, and now you lost some information about the total state, now you're going to get an entropy which is non-zero. So the idea, basically, is that you can use this to measure how entangled a state is. Because if there's a lot of correlations between A and B, when you erase B, now what happens is that you lose information about the total state. Okay, that's the basic idea. All right, so how do we... Let me just do one thing here real quick, just to remind one note from fresh. Just want to close a couple of softwares that I have open here. Should make things a little bit. It's not going to crash again. All right. So the idea here is that if the entropy is non-zero for a mixed state, once you partial trace the other side, then this means that you lost some information by erasing the other side, which means that this initial pure state was entangled. And of course, if psi is just a product state, then now, once you partial trace over one of them, what you're going to get will be a pure state again, so the phenomenon entropy would be 0. So basically, so S of the partial states can be used to quantify how entangled the how entangled the states are. The states sign is cool. So all right. Cool. No worries. I'm sorry. Lost focus here a little bit because I was trying to understand what this was, but no worries. Hopefully it's still okay. I don't know if I need to, well, whatever. Hopefully it's still working. All right. So okay, so how do we talk about quantifying entanglements? So there are many people that classify what an entanglement quantifier is differently. So it's usually, but not always, required that an entanglement quantifier satisfies. One, you most definitely want E rho to be 0 if rho is separable. Because you want it to be 0 whenever there's no entanglement, right? You want E of psi d to be maximal, some people require it to be log something, but in my case, I require it to be maximal. To be maximal. So the maximum value that this E acquires is for the state's ID, which is a maximally entangled state, which can be written basically as this. This only works in finite dimensions, of course, but yep. And then 3, you need E has to be invariant under applications of a local unitaries that factor as a U in A and a U in B, okay? This is for quantifying entanglements between bipartite states, so states with two different subsystems, right? So just bipartite states. You could generalize this more. I'm not really going to go into this. For us, what really matters is the negativity. So for us, is the negativity. Okay. What is the negativity? So before defining the negativity, let me briefly talk about Paris criterion. How much time do we have? Okay. Paris criterion, which is basically that if rho is a state, then this means that if you transpose this rho, it is going to be a state. Okay. So transposing the states will always give you a state. However, if your rho is a bipartite state, or so belongs to L H A H B. Now what happens is if your rho like Cij rho 1 sigma j, so this is always true. Now we define the partial trace over P as rho partial trace over B is equal to the sum over I and G of Cij rho I tensor sigma j transpose. So you only transpose the B factor, the second factor, right? This is the idea. Now, and it might be that rho TB is not a state. So basically, it's not positive. So if you transpose a density operator, you always get a density operator. If you transpose only the B factor of a density operator, sometimes you get something which is not positive. So the partial transpose is a positive map that is not completely positive. That's what we usually say. And then Paris criterion says that if the partial transpose of rho is not positive, then rho is entangled. So notice that the way back isn't always true, but for qubits, for 2 qubits, it is true. The way back is also true. So basically, a 2-qubit system is entangled if and only if the partial transpose of rho is not positive. Okay. And from this, we can define the negativity. So the negativity is an entanglement quantifier, a very nice one. Negativity is the negativity of a given state rho is given by the sum of the absolute value of the eigenvalues lambda I that are
Excuse me, I think
eigenvalues.
you meant partial transpose instead of partial trace in the other.
Oh yes, if I wrote it, I make this very yes. Thank you so much for this. It's partial transpose. I make this mistake very often for no reason. Sorry about that. Transpose, yes. Sorry about that. Yes. So it's the partial transpose, not the partial trace. Partial trace always works. Yeah. So yes, partial trace. No, partial transpose. Sorry, I always make this mistake. And thanks a lot for the correction. Whenever I'm saying it, yeah. Okay. So again, the negativity is the sum over the absolute value of the eigenvalues of the negative eigenvalues of lambda t. So basically, the sum over lambda I and the set, lambda p minus, where lambda p minus is the set of lambdas, which is negative, and which are eigenvalues. So it belongs to the spectrum, of the partial transpose. With respect to B or with respect to A, these two always have the same spectrum, the partial transpose with respect to either side, so it doesn't really matter. And we will use this as an entanglement quantifier a lot. Okay, so we will mostly use this as an entanglement quantifier. Cool. So this is one of the things that I wanted to say. Nice. Okay. What is okay? What quantum channels a little bit. Now, if you're very brief, well, this is already pretty late, and I think we're going to have to skip for this class, and I'll briefly mention them when they become useful, because I don't want to stay here for longer than 2 hours. And yeah, I still have a lot of I have a lot of content there that I don't want to share today. Then I'll share it later. Okay, so about quantum channels, the basic idea of quantum channels is that a quantum channel is an operation from that maps operators in one Hilbert space into operators into their Hilbert space. Okay, but more than this, a quantum channel maps density operators into density operators. And there are two conditions that ensure this, which are complete positivity and being trace preserving. So these are ensured by these are CPTP maps. And the definition of these two concepts are as follows. So if you take the trace over, sorry, we're using 1 and 2 here, not A and B. So the trace over 2 of epsilon rho has to be equal to the trace over 1 of rho, because rho lives in LH1 and epsilon rho lives in LH2. So this is the trace preserving part. And the other condition is that sigma tensor epsilon rho has to be larger than or equal to 0 for every sigma and rho which are positive. And of course, like these are linear maps. Cool. So this is what our quantum channel is. It maps density operators into density operators. These are particularly useful if you want to, for instance, talk about what happens if I want to map to send qubit 1 to qubit 2 through a channel or through a quantum field in our case. Okay. So we'll be mainly interested in two properties of these channels. These two properties are the classical channel capacity and the quantum channel capacity. All right, so basically the quantum channel capacity, oh yeah, let me give them their names. So it's C epsilon and Q epsilon. Basically the classical channel capacity, it quantifies the amount of classical information that can be transmitted through a channel, and the quantum channel capacity quantifies how much quantum information can be transmitted through the channel. So let me just write here. These quantify how much, or the rate, basically, the rate of sorry. Okay, sorry, the thing is not working for a second. Hopefully, yeah, okay. The rate of classical / quantum information transmitted. No, I actually a lot of the classical channel capacity and the quantum channel capacity, but I don't think that I'm going to give that much context. But basically, the idea is that you can consider the classical channel capacity as this bit rate, basically, with the smallest possible loss that you can think of for your channel. And that you can think of the it's very hard to compute it. It's very hard to define it, even, because you'll have to really define a bunch of information theoretical concepts, which I was kind of going to, but it's I'm not going to do this because we don't have that much time. I really thought that I will go faster through the rest that I have here, so apologies for that. But okay, basically, all right, the how to compute them. I'm going to focus on that. Okay, so the C epsilon, the classical channel capacity. There's a theorem that states that the C epsilon can be computed as the limit of n going to infinity of a quantity chi of epsilon when you apply it n times divided by n, and this this chi, if you're only computing it for the channel itself, not for many tensor product versions of the channel, then this is the maximum overall possible PIs and rho i's of S of the channel applied to rho minus the sum over I of pi S of epsilon of rho I. So this chi here is and this rho, of course, is the sum over I of pi rho I. So we're gonna optimize over all possible density operators, basically. Or the compositions of a density operator, this Holivu information quantity, which basically tells you the how well this basically tells you how well you can guess your system your initial state with an optimal strategy, and that's why it's so hard to define this. That's why I'm gonna skip this, unfortunately, because we don't have that much time. But basically, this is how you compute this. It means how much information you can actually transmit through the channel. And for the Q epsilon, here I'm gonna give a little bit more insights. Just gonna say that yeah. So the main difference between classical and quantum information happens due to correlations that the quantum system can have. So basically, I'm saying that it's entanglement, right? So correlations that the quantum system can have. So if you have a channel, the idea is that say that this channel maps a row 1 into row 2. Then there's this very nice theorem which states that you can always write this channel as being a unitary that is applied to your row 1 together with an environment that is in a given state. And then it spits out something which is a state for your environment. But the idea is that you can always write any quantum channel as being the trace over an environment for unitary that acts in the initial state and in a state of the environment. Okay? So basically, you can always enlarge your Hilbert space or think of any quantum channel as being a unitary that acts in your initial state and in some other state unitarily, and then it spits out the reduced state associated with the final output that you have. Okay, and this would be the raw environment would be the trace over the system 2 of something like the final the now. If you want to quantify like quantum information in the channel and things like this, what happens here is you ask the question, what happens if I have this third system, call it P, I don't care, which is, say, correlated or entangled with row 1. So say that this is entangled. After you apply this unitary and you shuffle the row 1 with the environment one, you're gonna get that if these two were entangled in general, now this entanglement is also going to be shared with the third system row E. So now, say correlations. So how much of this entanglement is preserved? So like how much of the initial correlations between row 1 and P will be, or the quantum correlations between row 1 and P will be preserved after you apply this quantum channel, and how many of them will have leaked to the environments? And this is basically what you're trying to quantify when you talk about the quantum channel capacity of a quantum channel, right? This is extremely hard to compute. So basically, before writing this, let me just like say that the so basically the question that we would be asking is what happens if we apply the okay, so what if we apply our channel, which is so epsilon is this whole block here, right? So epsilon, it's basically this. So what happens if we apply nothing at P, and we apply epsilon to rho, which is in 1 and in P, or in P and in 1, which is entanglement, or this is not necessarily, but yeah, which has quantum correlations. Now the question is, what correlations do we break, basically? The more quantum correlations we break, the smaller is the quantum channel capacity of this channel. Okay, that's the intuitive idea. I'm just gonna say that this is very hard to compute. I do not have any closed form expression that I'm willing to share with you. That's how hard it is to compute. And what I'm gonna say is that so for us, what matters is that if identity tensor epsilon applied to this rho 1p, where p is the third arbitrary system, is always separable regardless of whether rho 1p is entangled, then the quantum channel capacity of this channel will be 0. So basically, if you always break entanglements, the quantum channel capacity will always be 0. And indeed, there's a definition of what an entanglement breaking channel is, and I'll briefly state it if the computer responds, and it does. I'll definitely try to fix this for next time. Sorry about that. Okay, so entanglement breaking channel. And entanglement breaking channel is literally the definition is, well, if you apply the identity channel times your channel test product to rho A B is, if this is always separable, Q epsilon equals 0. But this is basically the definition. So it's a channel epsilon such that this is always separable. And it also implies in this case that your classical channel capacity is just going to be chi of epsilon. This is because if the output of your channel can never be entangled with something else, then the chi of epsilon tensor this just factors as chi of epsilon. Basically, if the output of your channel can never be entangled with anything else, this means that you cannot use this entanglement in order to transmit more classical information. Okay. All right. So
Rick?
I will talk about. Yes.
So I have a couple questions about this quantum channel, not definition, but statements that you have made. I'm a little confused about what Hilbert spaces does everything live when you write these functions. So this rho 1p, for example, is just for system 1, or is it the composite state for 1 and p?
Yeah. So rho 1p would be these two. Perfect. Yeah, great question. So that's why it can be entangled between the 1, which is our input, and p. So basically the idea here is, what if my input state is actually a state which is entangled with something else, and I apply the channel to this rho 1. Say that these two start entangled. if I always break this entanglement, and in the end, like, they always end up not being entangled and being in a separable state, now this means that this quantum channel capacity will be 0, right? So if you go to the statements of the... it stopped working again. But the statement, for instance, here, right? What I'm saying is, what happens if you do nothing? So this IP is like the identity in P. Maybe it would be better to write it as, I don't know, something like this. But if you do nothing in P, but you apply this channel epsilon to your rho, if you do this, what do you break? What quantum correlations do you break? So yeah, but this
And
state
I'm
here,
sorry, epsilon maps things in the Hilbert space of rho product with the environment with the space itself, or what does epsilon map from and into?
Yeah, so the epsilon, as we had it before there, it maps from 1 to 2, right? So the idea is it maps rho 1 to rho 2. Now, the thing is, if you add the environment, you can think of this epsilon as like a unitary, which is a simpler version of a quantum channel. It's just like a unitary evolution, if you will, of these two. But then you have to trace over the environment if you want to recover something which lives in rho 2. So that's why the epsilon, you see, the input is here and the output is here. Okay? Make sense?
Yeah, okay. But then, okay, that this epsilon of rho 1p will be a state that lives in H2, right?
Epsilon rho 1p is epsilon in H2. No. P is an arbitrary other thing. P is an arbitrary state which can be which we're considering to see up to which extent epsilon preserves or breaks quantum correlations between rho 1 and the system P. So P is completely arbitrary, right? The environment is kind of like the thing that makes us be able to see epsilon as a unitary. It's not really necessary for this discussion, I guess. You could see this as just like there's the epsilon which is mapping rho 1 into rho 2. And now if we apply the epsilon just to this, right? If we just do this, for rho 1 used to be entangled with P, now what is going to be the output? Is the output still going to be entangled with P? That's the idea.
Rick?
Yes, Daniel, please go ahead.
No, I think maybe what is maybe confusing is, I mean, wouldn't it be better if you actually circled in red, instead of including the endpoints of rho 1 and rho 2, actually included the environment and the rho e, because that's what actually you can just substitute for the channel, right? So if you take out what you circled in red and substitute by a channel, that actually you should actually not include the entrance rho 1 and the exit rho 2, but you should actually include.
Okay. Fair enough. Yeah. That's okay. Let me try to raise this.
And maybe, and also maybe because downstairs it's written IP tensor product with epsilon rho 1, but maybe with a parenthesis there, it would be clear also, which you use it in the last line.
Fair enough. Yeah. No, these are great suggestions. Thanks a lot. Let me try to fix this.
In the next page, actually, you put the parentheses, but here you didn't. I was confused too, but then when I saw the next slide, it cleared up. But here, I think it's missing a parenthesis, maybe.
Yeah. So basically, what the epsilon does is this. Yes, it gets an input from here and outputs it there.
But
yes?
shouldn't you include also because I mean the for a given channel, which is the environment and how it? Yes, I think that's what you can actually substitute by a channel, right?
Yes, but this E is arbitrary. But yes, I understand your point and I agree with it. Yes.
Yeah, for each C you can find an environment, right?
Yes,
if you want.
It's not unique. So, but yes, you're right. If you want to look at this as being the channel, then yes, you can see the channel as being like all of this bulk here with the initial state and the final state, and the final state not really, but and then you're gonna map row 1 into row 2, and all of this is inside the channel somehow. Yes.
Okay.
Yes, this is a way of
Thank you.
doing this.
Okay, yeah, I think now I've cleared my confusion also. This identity
That's,
times epsilon is just the map that you apply to evolve, not the final state that you're looking into.
Yes. This is the map that is applied. Yes.
Yeah, no, I understand. Perfect.
And let me clarify this here as well. Great. These are important things. Yeah, down here I actually used it as Danielle said, and I just didn't put the parentheses in the rest there. Fair enough. That's great. Sorry for the notation issue. All right, cool. Any other questions about this? Okay, if not, then let me say. So again, apologies for the third time. This is a very boring class. It's just like going through the things that we're going to encounter, whatever. And I just didn't want to break the calculations or the situations that we were considering in order to explain these things. I think it's better to just explain them now, and whenever we face these things again, then we're already kind of like ready to use them, or at least up to some extent. Just as a fresh reminder. I promise that the next class will be way better. Hopefully, I won't be a little bit sick as well, and I'll be less tired. But then we will really start considering the probes that couple to the relativistic quantum fields. We're going to talk about applications to the Andrew effect and things like this. And hopefully I'll be able to actually deliver everything that I had prepared, because today I didn't. But yeah, I'll definitely make adaptations in any case, and I'll also try to fix the technology issues that we had here. Everything was very laggy and annoying. I'll try to fix that for next time as well. All right, so yeah, thank you so much for watching and being here today. Again, apologies for the very technical like listing of results. We'll stop doing this from next class tomorrow.
Excuse me.
Yes.
Sir, would you please repeat, as I couldn't understand, about the information, lost information in one of the space. Would you repeat again that if we lost information in one of the spaces, what happened to another one?
I guess that what I said is that if you have your system and the system is correlated with another system, now you apply your channel to this system. The question is, how much will your final state here be correlated with the other thing? Because you can't like increase the correlations by applying a local operation. You can at most decrease them or like keep them the same, right? So basically, the quantum channel capacity is trying to estimate how much you preserve the correlations between your system and an arbitrary system. That's the idea. And how much you can use this in order to transmit quantum information, things like this. But in a way, quantum information relies on this idea of using and exploiting these correlations. So that's why it's so important to preserve the correlations between your system and others. Does that help you? Is that what you asked?
Yes, thank you. Because in entanglement, in channels or in spaces, I was a little confused that when we lost one of them, what happened to the another one? And thank you very much.
All right, no worries. Hopefully this was a
And
little bit clear.
sorry, about the is there any attendance list? I don't know, because in the
I
email
think it was in the
mentioned.
chat here. I can copy paste it in case you joined right after. So this is
Yes,
the
10 minutes. 10 minutes. Thank you very much.
no worries. Okay, cool, amazing. So see you guys tomorrow. Thanks, thank you so much for joining today. And yeah, all right. See you tomorrow. Let me stop the recording.